Good afternoon, everyone. It's end of the day today, but I see many faces, so thanks for being here. I'm Sanjay Goyal, one of the architects in Microchip. We have a data center division, or DCS, and I would like to take you through the overview of our first serial memory controller, SMC 1000. Thanks to IBM team, they have been really good partner. Okay. So with this chip, we entered memory infrastructure market for high performance data center computing. We announced it in FMS, and we believe it's the first of its kind. It enables CPUs and other compute-centric SoCs to utilize 4 times the memory channels because we use 8 lanes of OMI, which is about 34 signals versus you need 150 DDR signals if you need to connect to parallel DDR4 interface. So roughly 4 times the memory channels we get if we use OMI interface. It delivers high memory bandwidth, and interesting part is that it gives you media independence for these compute-intensive platforms with ultra-low latency. These are some of the offerings DCS has. We have been in SAS and PCIe business for many, many generations. We've been contributing to many specifications, and we have endpoint solutions, which are our SSD controllers and the NVDIMM drives. And with PM8596 or SMC 1000, we have entered memory infrastructure now. So why is this becoming an important thing? If you look at this graph, memory latency per core is increasing because DRAM buses are limited in number, and number of cores are increasing with every generation. So the DRAM buses are not scaling as number of cores are going up in number. So IO bandwidth per core is going down. So this is why having something like OMI is very important for next generation SoCs or CPUs. The emerging memory infrastructure market has need for near memory innovation and far memory in composable architectures. We believe PCI and SATA interfaces are not meant for memory expansion. So OpenCAPI is one of the very low latency, high bandwidth interfaces for memory expansion. There are other protocols coming up, CXL, Gen Z, which would probably coexist with OpenCAPI. So you might have seen this slide in other presentations. It just emphasizes that we need increased memory bandwidth, we need media independence, and we need lower solution cost. So we get it all with devices like SMC 1000. So how do we get more bandwidth? It's because we are able to pack or have more channels, more OMI channels for the same number of pins. As I mentioned, 32 pins for 8 lanes of serial interface and 2 for clock, so 34 versus DDR4, which requires about 150, 160 signals. We can pack many more OMI channels versus DDR interface. And then it gives us media independence, and I think it was mentioned by IBM person that the SoC packaging, you don't need, if you're not having as many DDR channels, we don't need as many balls, and the SoC size, package size also goes down. So just emphasizing it further, you can have LPDDRs, DDR4s, GDDR, and then you are decoupled from CPU innovation. You can have it independently independently developed. Lower solution cost, as I mentioned, the package size, if you would like to have similar number of channels, because of number of pins, less number of pins required, the package size would go down, which results into overall cost saving. So just emphasize that. This is the block diagram of SMC 1000. On the left side, you see OpenCAPI or OMI, 8 lanes, which goes through OpenCAPI data layer, then goes through the transaction layer, and then into the memory controller. And on the other side, we have DDR4, 72 pins at 3200 mega transfer per second. MIPS processor is for the boot up of the chip, for error logging, and we have root of trust on this device, so it provides us with security aspects. We have hashing and we have integrity RAS implemented, and there are a few peripherals to boot up, to help us on boot up, and for the temperature sensors and controlling the voltage monitors if needed. This is the feature list. We have 2 modes, 8-lane mode and 4-lane mode. The PHY or the SerDes are OFI 28G compliant. They're running at up to 25.6. So there are 3 different rates they run at. And the OMI interface supports dynamic low power mode, which means if the bandwidth required on the interface is not 25 gigabytes per second, you can reduce it to 8 lanes to 4 lane or up to 2 lanes with very small, within a very small time factor in nanoseconds, not even in microseconds. We support up to 4 ranks on the DDR memory interface, and we support 4, 8, and 16 gigabit memory devices, and 4 ranks or 3D stacked 4 high memories. There are hookups in the device for persistent memory. We are going to open source the firmware on this device. And the purpose of the firmware is DDR OMI initialization, in-band temperature, and error monitoring. ChipLingo is our industry standard tool. We share it with all our customers to do the debug, to look at the SerDes eyes. It's just a very nice debugging tool. Security and data protection. We have hardware root of trust built with boot ROM. We have secure boot and secure update, means firmware updates are also checked for integrity and authentication, both actually. Single symbol correction and double symbol detection, it's on the DDR interface, over 64 bytes, 8 bytes of ECC is sent into the DDR media, and SecDAT is implemented part of that. The DDR controller also has this feature of memory scrub with auto correction on errors. It's a really small package. If any one of you got a chance to look at a smart modular booth outside, it's a 17 by 17 package, and it's a very power optimized chip. It's peripheral support as just for the temperature sensors, voltage monitors, and debug. Few more items from the feature list. This chip supports chip kill if you use by 4 DRAM devices. It has data integrity throughout the chip required for enterprise applications. And less than 64 byte writes result into read modify write, so it's all handled in the hardware in the chip. There is protection against address collision, and it supports DRAM sizes from 16 to 56 gigabyte. which is a big range. And this is the DLPD, or the dynamic lane power down feature, that OMI link dynamically can switch between 8, 4, and 2 lanes. And this saves quite a bit of power. So this is the chart on latency. We are very proud of our partnership with IBM team, and we are able to achieve a very low latency, which is just 3.94 nanoseconds extra loaded latency versus LRDIMM. So a lot of work went into it in achieving this, and this is probably one of the big features of this device. So these are the applications, DDIMM application, and on the left side is what we have from a smart modular team. And just showing the comparison in size of RDIMM versus 1U DDIMM. Other DDIMM providers are Samsung and Micron, and the sizes of DDIMMs are 1U and 2U. Other applications are chip down application, and we have been able to validate DDR4 running at 2667 in this mode. And this is the last application, which is NVDIMM-N Application. So we have hooks, but there is a lot more work which is required to make it work. Okay, this is my last slide. Thank you. Any questions?
What kind of information is available through the DDIMM?
So it can read the registers, write the registers. SerDes I can be plotted, 2D diagram. We can extract the logs and show it in user readable format. So those are some of the features.
Could you please go back to the latency slide?
3.94. So what we compared is how long would it take for the read data to come from the left side? Okay. So left side is the LRDIMM picture, and the right side is what is with SMC 1000. On the left side, once the read reaches the DRAM and the data hits or comes to the C4 bump in the device, how long does it take for it to pass through the memory controller? So we counted the latency through that. And similarly, when we get the data on SMC 1000's DQ pin bump, from that till it comes out on the OMI C4 bump, how long does it take, the latency? So doing the math minus SMC 1000 latency, true latency minus the LRDIMM scenario latency, that's how we arrived at 3.94. So most of it is coming from SerDes delays. In case of SMC 1000, we have SerDes on the SoC and SerDes on the SMC 1000. So that's where the bigger difference is. In both cases, you would see there is memory controller, there is DDR5. So most of that is very comparable. The added latency is coming from the SerDes transmitter and receiver.
But it's not a fair comparison because we're using the LRDIMM. You have to compare against the UDIMM and the unbuffered DIMM. So that will be 4 plus.
I think
6 something.
Okay. So from that perspective, we have to see how much memory are we able to address or access through LRDIMM versus through UDIMM, right? In case of UDIMM, yes, we are directly connecting media, but we are able to go up to 56 gigabyte size running at 3200, which is what you can achieve with LRDIMM. So that's from that perspective.
Because your connection is much shorter than on the motherboard.
Yes.
What is the latency from the OMI service to the memory controller? Just something showed up at the OMI interface to something showed up at the the AXI, let's assume it's the AXI interface in the memory controller. What is that latency? Inside.
Can I tell it to you outside?
Okay.
Yeah, there are certain changes we had to do in all our IPs to bring it down. So, I'm afraid I cannot tell. Any other questions?
Just one. Are the all GPIOs accessible by the host
Yes.
as a registered map space?
Not at a register. Okay. So we have extracted using the firmware on MIPS. We have created APIs for pretty much all the resources on the chip. So host now has access to all the registers in the chip. It's better to communicate with the MIPS firmware because it is sort of the master for all the resources on the chip. But it has direct access.
It has direct access, but it is very good with API.
From users' perspective, yeah. Anything else? Okay, if not, thanks so much. Thanks for your time.